Yeah. So we're live, and you can see
Okay.
all the people in the text editor that have joined. And how about we start introducing ourselves, just like 1 minute of like how you got into theorem proving or interested or heard about it the first time, and what's your name, and do you have any hobbies outside of work and theorem and or theorem proving?
Yeah, I'll start. So hello everyone, I'm Paul. So I got into theorem proving when I read Edwin Brady's book on Idris, and then I started a study group when we read a book called The Little Typer, which it talks about dependent types and proofs, and then moved on to Cog. And in my day job, I'm building a language called Juvix, which will eventually have dependent types and proofs. And outside of work, I love music. I love Bach and opera and ballet, and I like reading like historical politics.
So I'm Jan. I have a background in computer engineering. First, I was only programming C++. Eventually, I got to meet Haskell, which I thought was very cool for its syntax. And after that, I went to Chalmers because I was very interested in functional programming. And then in there, I started using Agda. And learning Agda was fascinating. I learned how much you can do with the programming language. So that's why I got hooked into proof of systems. And outside of that, I like music as well, same as Paul, mostly symphonic music. And also I like to spend a lot of time in my computer trying new things like Emacs plugins or new command line interfaces, something like that. Yeah.
So I'm Jonathan. I got interested in functional programming in my master's, where I had the opportunity to work with automatic theorem provers, and there I got my first experience with Agda, this dependently typed functional language, very exotic, unique in some sense. And after my master's, I attended to some seminars in homotopy type theory, and I got interested in the connection between mathematics and computer science that was evident in this kind of dependently type programming language, which is, again, is a bit exotic again. And I'm writing a PhD dissertation on that topic related to formalizing some math in HOT. And and I got the opportunity to work in this functional programming language that we call Juvix at Heliax. And we are taking a lot of inspiration from Agda and other programming languages to create this language. And besides that, I usually like to read history of different kinds, philosophy as well sometimes. And when I'm not in front of the computer, I like to pet my cat, watch a lot of TV series, especially crime series, suspense, thrillers, and sports. I like to play tennis because of my wife. I have to. And and I recently start going for bouldering, which makes me, well, we will see, stronger, right? But it's kind of challenging. But yeah, that's me.
Hi, I'm Niels. My background is in mathematics, and then at the end of my PhD, I decided I wanted to go into software engineering. That had always been a hobby, and I thought these dependent types were really great way of satisfying some of my mathematical desires, so to speak, and also do some programming. And I joined a study group with Paul and Walter where we learned about Coq. So that was a really nice time. And outside of this, I really like playing piano. I do a lot of running now. And I also like learning languages. I'm currently learning Swedish, for example.
So I'm Lucas. My background is broadly in computer science and computational logic, and I don't remember how I got into that. It's been a long time. So I actually did some research in, like, let's say, some aspects of type theory, particularly automated reasoning in type theory. I'm actually the main author and maintainer of this Coq-Hammer project, which is an automated reasoning system for Coq. I know Coq quite well, though I've never tried Lean, and I'm quite interested in it.
What do you do outside of work or theorem proving?
I don't know. I go hiking. I read books. I don't know. I relax and not think about computer science.
Very cool. Yeah, and I'm Walter. I didn't know what functional programming was until I was working in industry for about 4 years. And then someone said, oh, there's this language OCaml, and what? And I'm like, what is OCaml? And they're like, it's a general purpose programming language. And I'm like, no, it's not. I know all programming languages. And yeah, boy, was I wrong. And then I got really interested in Haskell. And at ICFP, I was sitting at breakfast one day at this functional programming conference that I really enjoyed going to. And the person was like, oh, have you heard of Coq? You can prove programs are correct. And my mind was blown. And so when I moved to London, I met Paul and Stefano and Niels, and there was these study groups about dependent types using the little typer book and Coq art book. And now I'm interested in Lean as well. And outside of work, I like to play guitar and also watch a lot of series. Like, I watch way too much TV. I mean, yeah, it's crazy.
My background is, as most of the people here, computer engineering. I work in the industry for more than 20 years. I discover and love functional programming, actually with the discovery of Underdog for reason that I still don't understand, because the language I think is great. The community is F#, because I was doing a lot of C# code and use a lot of link and to improve. Anyhow, I start to read about sharp functional languages, and I go then down the rabbit hole. I work with 2-3 companies, still working mostly with Scala and data. And I met Paul and Walter trying to understand something of this weird, very nice book about the little typer. And I really get into this, try to theorem proving and stuff like that. So much so that actually my part-time, in the few spare time that I have, I'm actually studying mathematics now to improve my very bad take of mathematics during my university. And that's it. I don't have so much spare time left due to having 2 kids and studying, and maybe my interest towards cryptography and cryptocurrencies. So that's mostly me.
Today we're going to translate like this piece of Haskell up to here. So it's kind of a small expression language, but some of the expressions can read an input, right? So we have these variables in our expression, which means they can evaluate the different things depending on what the input is. But some expressions are constant, so it's just like a normal expression. And then the other kind of weird thing is that this expression language needs to be extendable. So it's not just a big OR of expressions that we know exist, right? The user can add their own expressions as well. So, and this is all kind of described in the blog post on symbolic derivatives for symbolic automata. All the info is here. All the links. Wow. Never type on camera. Yeah, so they're all there. So if you're missing some background, I would go look there. So let's start. This is the data structure that's used to, it's almost like the abstract syntax tree of these expressions. And we kind of need them so that we can compare expressions for when we do simplification of the expression tree. For example, if we have A or B or C and C or B or A, then we would like to be able to sort the one or to also be A or B or C. And then to sort it, we need to be able to compare them. And then we'll see, oh, actually, the left and the right side of the AND is equivalent, so we can remove it. And the whole expression is actually just equivalent to A or B or C. So let's start by just translating a data structure to Lean to get used to the syntax. I want to copy this to Lean, and this is our Lean code. And I'm just going to comment it out. So we have a main function that just prints something, and we can evaluate it. So this is what this hashtag eval says. And then on the right side, you can see the evaluated function. Right, prints out hello Twitch, and so you can do like proper imperative programming here, but that's a story for another day. This was just a way to start. So does anyone want to try to type this in Lean? Okay, Jonathan is starting.
Jonathan is
Cool.
Oh, yes. I think from the link that I passed, it seems like I should use this keyword, then where, right? Then using the pipe symbol, you separate the constructors. I guess we have...
It's record type, right?
Yes, it's a record type. So we have,
there is no...
We only have one constructor.
So is here record? The keyword?
I think you can say structure.
Oh, okay, structure. Yeah. Okay.
Yeah, cool.
Do we have the string type?
Let's assume that either way for now. Even if you get the syntax error, let's run with it.
Right, okay. Hash.
So I think since they're like not separate constructors, we can get away without the pipes because we're just declaring fields.
So like this?
Yeah, yeah.
And I guess we have here a list of descriptions.
Yeah, yeah. Let's see if that is even possible. Yeah.
Invalid field type expected. What?
Yeah.
Boolean.
Yeah. Okay. Let's see what's wrong. So the descriptor is unknown, but otherwise, I think the syntax is correct. We got our syntax right. So we already have a problem where it's hard to declare a recursive structure, right?
Mm-hmm.
So I think we might have to go with the inductive type. So we have to find some syntax.
Okay.
For that, for
Can I try
multiple fields as well?
Can I try just this thing, maybe?
All right.
That will work? No? Like defining the symbol and then declaring the fields? No, I think...
No, I don't think that
doesn't still work. Okay.
So we can, okay, so the manual says, by the way, so I'm just looking it up,
Yeah.
Structure is a special case of inductive data type. It has only one constructor and is not recursive.
Oh,
But could we do something like this? So you've got only one constructor, maybe something like this. And then it takes a string, it takes a net, it takes a list of tests, and a bool. I also don't know the Lean syntax, so maybe this doesn't make sense.
No, I think.
But this at least captures the data, right?
Yeah, but it would be nice to name the parameters.
Yeah.
So I think you can do this by just moving it here. So I think we can just move these parameters here, right? Just before the arrow, and then they have names.
Yeah, I think that makes sense. Wonder if you can access them then, though.
Yeah, probably not. I think it's probably just for readability.
I guess you need to write your own accessors.
I think
so. Ultimately, there should be like some way to automatically generate those accessors.
Yeah, for structure there is.
Yeah, so there should also be for inductive, but I guess now you just need to write it yourself.
There is some word for this constructor that is like the default word if you only have one. I think it's intro or something. Like Lean has a convention.
Right, okay.
You use the word intro.
Yeah, for the one constructor, yes.
So we've translated this data structure from Haskell into something in Lean, and using the intro convention, that's like the structure keyword here would have been great, but we can't do that with recursive structures because description is recursive. We can't use it. So we'll lose a lot of the things that it would have auto-generated for us, which is kind of a shame. I think maybe we start with some hashing functions, just to write some functions. So we have these pieces of Haskell code. And so maybe we start just by hashing a string to a net. I'm quite happy that...
you need to define the functions before to use them, or they can be mutually recursive? Okay.
Yeah, I think so. But I haven't tested it, so, but let's assume so and then try to swap them and see how it probably breaks. But yeah, I'm really glad Lean stole this piece of Python syntax. Because it is a definition, right? So yeah, we just take parameters, so and we return a net. I think it's colon equals to actually start the function. So we just return 0 and then go eval hash string a. That should give us 0. I love it when I don't name parameters. So there should be the accumulator, right? Basically, for the initial one, and then the list. Oh, we have int. So we can just use int instead of net.
Yes. And it has coercions, I think, as well.
Yes.
So
yes.
You don't need to worry too much.
So is not the unary natural numbers and int some sort of primitive, or how are they defined?
Yeah, let's see if we can find that.
It says the nat type represents natural numbers, arbitrary precision, unsigned integers. There are no overflows. It doesn't say how.
Are they efficiently compiled, or do we care about that?
They are more efficiently compiled, yeah. So
Okay.
It's defined as an inductive type, but when it's compiled, it's optimized.
Mm-hmm.
So they are using GMP, the standard, like it's same that Haskell uses.
Right.
Cool.
So if we don't want negative numbers or we don't need them, let's just use NAT.
Yeah, you can just use them you can just use them
Yeah, I
without
think
worrying
so.
about
uint, okay.
Yeah, I was just checking. Maybe. No. Okay. But
you
yeah,
can open
then
the definition.
Sorry.
You can open the definition if you want. There is in the basic Lean.
How do I do it?
Yeah, like this, and then press. Yep.
Oh, nice. That was just command click.
Yeah, command click
Yeah.
or Alt, depending what you are.
Okay. So we can just use a NAT since we know the hash is not going to be negative. Yeah. And the NAT is also compiled to something efficient that I forgot, unlike in most of these languages. So that's, yeah. Okay, let's stick with NAT. That's good. So I have our accumulator and our list, and what do you call this? Or the zero. And so now.
Is it not going to conflict with?
Sorry?
Is it not going to conflict with the zero?
I think you need to use match, no?
I already kind of matched them here.
This is a pattern. It's not a, I thought this was a variable.
Which one? This is
zero in the yeah, exactly here.
Yeah, it's a variable.
Oh, it's a variable.
Yeah, I don't know what to call it. It's the init, like.
Yeah.
Yeah, or let's be very British and just say init.
I think the question was whether you could use zero here because it potentially shadows the constructor in NAT.
Okay.
But we don't know whether that's true or not.
Yeah, that's a good question.
But it was interesting to know whether it does.
Okay, I'm just guessing syntax here at the moment, so it seems less NAT work, so that was good, but
that's happy.
This didn't work, so maybe also like Cockit has some notation to import that I don't know about, but let's go with this for now. And now I think their lambdas starts with fun like this.
Yeah.
And let's see if it has multiply. And then oh, great. We can command click on full now. Oh, here we go. So init, that was the word. Okay.
Yeah.
And the function is first, and then the init, and then the list. Okay, good. Yeah, I think it's that. Yeah, that compiles.
Great.
So then this can be hash list 0. And now we have to turn our characters into nats. Well, there's a nice search actually. So I think I can show that here. So when we're on this site, so this is a Google search here, which is probably useless, but the type ahead looks pretty nice.
Can you share the
chart to net? Yeah, so I think this chart to net is probably what we're looking for. And I really like, for me, this is so important that a language has click to source. I don't know. It's just.
Yeah.
So we can actually just read the code as well and not rely on documentation. Yeah, there's a string.
Also, it has a data field. A structure string has a data field, which is a list of char.
Yeah, or you can just string to list here.
But why is it OM?
Because it needs to convert.
Yeah.
Let's see. Oh, in. Oh my.
Well, because I suspect that like when they compile it, then like you have the source code here, but
yes,
it really
yes.
gets compiled to something else. So
yeah,
then the conversion takes off. And
yeah,
You're right. So yeah, then it's good that it's a explicit function. So yeah, that we know we're doing it. Okay. So now hash string gives us 97.
Yay.
Which is probably right. And AB would give us 3,000. How big can we go? It's pretty fast.
yeah.
That's pretty fast. Okay, cool.
That eval thing is quite nice. The fact that it updates when you type, you don't have to do anything. You just show you the results immediately. It's like having a better REPL.
Reactive REPL.
A reactive REPL, yes.
And we can just hash with the name, right?
Mm-hmm.
And the params, which is a list like this, and we get our net. And this is just hash list of, I can almost copy this code, it's so close.
Does it matter if the if the parameters goes after the colon symbol, or what is the difference?
Yeah. Okay, let me show you. Okay, so this, let me first show that we have to have the names, after they've been defined. So we have to move this.
It's because okay.
Here, okay. But now let me answer your question as well. So for example, if we did this, right? This is what you're saying?
Yeah, with the S as well.
Yeah, so then we just have to do this.
Right, okay. So you need to do it before the colon if you want the labels.
Yes.
For the parameter, okay.
Exactly. Cool. This is name, and this is params, but
by the way, getting back to the question just before, I think this is actually different in Lean than in Coq. I think I saw that. So I think you can actually do the name after the colon as well.
In Coq.
Yeah, so yeah, I was also surprised. Yes,
okay,
that also works. But probably you still have to do the lambda.
Out of the type. Oh.
So you still have to have the lambda.
The first test is not used. Yeah.
So yeah.
But I think in Coq that was different than in Coq, because I think in Coq you couldn't write the thing. And also if you get dependent types, I think that also matters a bit.
No, I think you can. It's just like a different syntax. You need to write those for alls everywhere. So you can do essentially the same thing. You just need to write this for all.
You can do the same, but yeah.
Which is inconvenient for like programming to write those for all everywhere. But
we need to figure out how to access this hash field from the inductive type descriptor. So
maybe it's with dot.
Very lame is just get hash. But I know with structures we would just be able to say dot hash. Maybe underscore,
Underscore, yes.
Yeah. But in the meantime, I'm gonna, if anyone finds something better, that would be great. But
can you just use the dot syntax with an inductive? Oh,
with
but
structure.
no.
But
oh, yeah. Yes.
So is there a reason to use the underscore here?
Yeah, exactly. I had the same question.
no, good question.
I mean, in the name, get hash instead of camel case. Oh, is this Unicode or is this?
You can introduce Unicode.
Yeah, this is Unicode. So this
is real Unicode. It's not the editor tricking you.
Yeah.
Okay.
Yeah, this is
Nice.
is basically backslash and this, or oh, sorry, no. Let me just double check. Yeah, backslash and this character.
Mm-hmm.
And if you surround something by this, then you don't have to specify the constructor which was used.
Mm-hmm.
It infers that for you. So
Okay.
yeah, I don't know if I like it or not, but
so let's say that you find the symbol and you want to know how to type it. Do you know how to do that?
yes. So
okay.
If you go, I knew this. So Command Shift P, lean, then you can open the documentation view here, and then abbreviation cheat sheet is right here.
Okay.
And then you will find a lot of Unicode symbols here.
Oh, good.
It should also be like a pop-up, which is just pops up when you hover over this symbol and tells you what that is.
I think it's like later.
We can borrow this list for UX.
Yeah.
Yeah. You'll probably like end up using 12 of these and just kind of I don't know.
Don't underestimate the users.
Yeah, actor hackers will want to use all of these.
And the ones that you cannot see as well.
Yeah, those are my favorite, the invisible ones.
What they expect when you use type variables, they expect you to use these.
Yes.
This is the
that
convention.
seems to be the convention, yeah.
Like mandatory or?
No, it's just...
No, I think it's conventional, yeah.
Okay.
But since it's just /a, it's kind of easy to remember these ones, so might be okay. We can now write our constructor for our function. Hash with name and params and list.any. We need get reader as well now. So just write that here until we figure out how to do this better. No? Oh. What's wrong?
Maybe indentation, I don't know. That's it.
I think you can do this. Takes a list and a predicate.
I think the other is...
Oh, okay. Good. There we go. All right, so this and this is equivalent. What's next? This is kind of the same. The reader is always true. Let's just make this intro reader disk. And it's the same, and except this one is always true. but that's the only difference between these two functions. I was just finding something interesting. So remember, we can just eval things, and then they're printed out on the right.
Mm-hmm.
Well, yeah, that's not always true, right? You need to, for your class, you need to implement the wrapper type class, the representation.
Oh.
So, but luckily, we can just say deriving wrapper, and then it derives it for us, and then we can see it printed out. So
great.
Cool.
Yeah.
Even works for non-structures.
Yes, that's what I was surprised by. So I'm happy to report. Yeah, some things still work for things that aren't structures and works recursively. So this was very good to see. We want to write this compare function, but to do that, we need to know that ordering is a monoid, because we want to use these operators that short circuit, or like we can just use a lot of if then else's. So I found that monoid is in the standard library, so that's a good start. I guess now I want to know if ordering is there. Okay, good. That's another good thing. Okay. Now, does it implement monoid? That's here. So instance, I think it's just colon, and then we say monoid and order where, and then.
Yeah, the top two were missing from, but maybe that's because they came from semigroup or mul1 class.
Ah, yeah.
Well, it seems like the source is different from the documentation. Like if you go back to the documentation, it doesn't extend mul1 class; it extends one.
Ah,
yeah.
So there is some discrepancy here. Maybe it's like different versions. The different version of the library is linked to in the source.
Maybe let's try semigroup first. That should be very simple. Yeah, so we're just going to say ordering is a semigroup. So it has
Can I ask, what is the motivation to define these instances?
Yes. We have this function. So this is
for comparing, right?
Yeah. So for short circuiting compare. So we can do if then else's a lot, but then we would later come back because it would just not look very nice. And yeah. And now it's like an opportunity to look at the proving syntax. So just want to see if the syntax is correct first. So A, B, C of type G. I think colon. This syntax still incorrect?
I wonder if we need to import something.
Okay, let's see. We were in.
Yeah, probably this one, algebra group.
No.
I think we just need to write it.
I think it's just less than with like two orderings.
It needs to return an ordering though.
And
right?
needs to return
semigroup
ordering.
instance. Yes.
So what is the syntax for pattern matching in Lean?
Oh, we
Match.
can
Match X with match X with.
Okay.
Yeah. Q Y and otherwise
Underscore.
Not underscore.
Not underscore.
Why not?
No, I think it's not there.
I'm offended. Like,
Maybe just remove that. No, line.
Is there otherwise? Oh, you just want to.
No, I think it's complaining about the whole. Because EQ is not the constructor.
It's like a symbol here. It's not a symbol.
And that's why it complained about the whole other.
Mm-hmm.
Yeah.
Okay.
Perfect. All right. So then this
TEQ is a type, isn't it?
EQ is a constructor for ordering.
No, the uppercase, it's a type.
I think it's just
Yes.
I don't know, but I think it's just like
Doesn't think it exists.
Yeah.
it's just interpreted as a variable, which
Yes.
got everything, and that's why the second case was redundant.
Yeah, it was basically like saying X. And then, so let's just see this error again. And then we said, oh, if it's not X, then, and then it was like, well.
Redundant. Okay, yes.
Redundant alternative.
Should have read the error message, yes.
We've caught every possibility here because X was a variable. This could have been like Z. And then, so it like, we were just capturing all possibilities in this. And now we've got the right constructor. So we're not catching all possibilities. We don't have LT and GT, which will be captured here.
Yeah.
And now we're not getting the error for multiplication since we have an instance of multiply. Okay. So we can write this as a theorem. And what's nice in Lean is the syntax is exactly the same for functions and definitions. So for definitions and theorems, sorry. I'm going to just put this on the next line to make space. So we can just write theorem here. And then we write by to say we're going to start using tactics. Otherwise, we could just write code. Like I assume Agda works. I don't have any experience in Agda. And then we can write, say, sorry. And it's like, yay, it's done. But this is a cheat. And I think there's a warning somewhere here. There should be a warning.
Yeah, I'm surprised it's not more prominent because it says goals accomplished, right? But
very happy about
there is the
status bar. There is a problem.
Here we go. And here, like the squiggly thing says
no quick fixes available.
Sorry?
It says no quick fixes available, which is fair enough. Yes.
Oh, yeah. All right.
And then you're in conversion mode and you navigate around.
Yeah. So now you could say
so LHS.
Yeah, left hand side. So now this is your state.
Yes. And then
It's weird. And then you can say conger, which breaks up the multiplication into these two things. And then you can say riffle, which, why? You know. So these are my two goals.
Yeah, so you want to say so I've got hypothesis A, B, and C.
Yeah.
Yeah, I don't understand what's going on.
Understand this tactic state. What does that mean? A times B is not a proposition. What is?
Yes.
Yeah, and like I don't see how we can just go riffle and it's okay, apparently.
Maybe another riffle because you have the second subword.
What?
Why have we proved?
No.
No.
Are you finished now?
But
So is this conf like a fancy rewrite, or what does it do exactly?
yeah, I'm not.
It's basic navigation and rewriting tactic.
Right.
Yeah.
So if we type raffle, it just gives back the same expression, so it does nothing.
Yes. So there's no rewriting. So it expects some rewriting to happen inside.
Yeah.
And you're just kind of exploring the graph of where you want to rewrite. That's what conf is doing.
Okay.
Yeah. Now
So maybe
we want the right-hand side to rewrite. We want to rewrite the right-hand side.
We need to match on A, and then either using comp or another tactic, try to simplify that.
After the assignment symbol, yeah.
Well, after matching on A, otherwise we cannot evaluate it.
But I think you can use some kind of destruct A instead of matching.
Yeah.
Well, it's the same, right?
Like we were doing here. Well, this didn't work, but this
I wouldn't say, yeah, it's the same, but this is like a more Haskell stuff, Haskell style that using the tactics.
Okay, but so all these proofs we have kind of rely on multiplication being commutative. So maybe we start by proving that, because that hopefully doesn't rely on another proof, and then like we'll have the same issues.
Yeah, I think
we'll get some.
We can just like, you just should distract A, and then this should be like, maybe let me try like a buff here. Maybe let me try to do something. Let's just do the basis A.
Wait, you think you have to say bye?
Yeah. What happens then?
Oh, that finally did something. Yeah, look at this. Oh, before the comma.
I don't actually.
Look here on this side. Now we have the cases on the right.
We still need to simplify.
Yeah, and now you need to simplify. Just compute this thing. So like some ref.
Well,
reflexive.
I wonder if we do a comma there. I'm not sure.
Or is exactly the meaning of the comma?
Oh no,
like
we
chaining together.
If you want to check, you have to use this syntax.
EQ.
Yeah.
QT.
But
I think your idea is fine, Walter, to define the mul com outside.
Okay. So let's see. I just want to check what is net. This one. This doesn't look like it's going to accept symmetry. So
right, but in our case, we'll be just matching on the first argument and proving with raffle.
Yeah.
I proved it.
Use
Proved it. This was just raffle was the wrong name. RFL.
Oh wow. So
what is the semicolon?
It applies, I think, to all subgoals. I don't know what this is.
Yes. Yes. So this is the equivalent to the semicolon in Coq, where this one, it means something else.
Okay.
That will only apply to the first goal generated after cases A. But
yeah, so now we have two subgoals. And what is a comma?
Yes. So I think you can then do.
What does a comma do?
Yeah, that is a really good question. What the comma does.
Assuming a variable. No, okay, so maybe let's comma is yeah, you can do this as well. Yeah.
Yeah. So this goes case by case by case.
Mm-hmm.
Which
what do you
have?
Mm-hmm.
This is not allowed. Okay. And what if I
maybe you should do some, I don't know. But we have a comma there, so maybe it's not a comma. It's this.
Yeah, I'm wondering if we can get away with a comma, like because all the other examples
seems like
I have commas in it in the documentation.
Okay, I didn't look at the documentation.
Well, that is so weird.
You can actually write it more nicely. You can like specify.
Yeah.
You specify like you can write cases with and specify like what you're matching on.
Yes.
You can just do case.
Yeah, you need a split. You can put split on top, or you can do the matching as you were doing. I can't write because I still. Oh no, wait. I can write now. Try.
Oh, this works. This worked.
Ah, okay.
Mm.
I'm wondering why this doesn't work.
Because match is a term and you're in tactic mode, so.
No, you just say buy and
Yeah.
no, I'm sorry, I'm on 105.
No.
That's
no, you need to probably do something like this.
Yeah. I've never had so many proofs, 2 proofs going in parallel.
Never seen that before.
Productivity.
Yeah.
The
same terms in the same order. But
sorry, I didn't.
Yeah.
I was like so engrossed that I didn't notice that we probably something else now.
Yeah.
Yeah. So here you need to match. So the way I would prove it is I would just do.
Just one parameter, probably.
No, just whatever. The most dumb way of AP. Didn't work. I think you need. I don't get it. What does it say now?
Unidentifier A. So this needs to be in the name. And I think you also need intro.
The form.
Yeah.
What is intro?
Why doesn't it work?
Oh.
No, what is intro again?
Yeah, intro is basically the same as fun in im.
Oh, okay.
Why does it say unsolved goals?
Let me just see. Maybe I got the syntax
But
wrong.
that should be solved because this is but I mean, yeah, but the theorem is not true because the theorem is not true because if one is LT and the second one is GT, then we always return the second one. So yeah, the theorem is not true. We are trying to prove a false theorem.
Oh.
Are you sure?
Yes, I'm absolutely sure because if you scroll to the less than and you take X as LT, it basically tells you.
Oh yeah, it's not symmetric. That's true.
Yeah, if you like go back here and try to do this proof, then it's and you scroll down, you see unsolved goals. So those unsolved goals are essentially the counterexamples.
Yeah. Because less than times anything is less than, and greater than times anything is greater than.
Yeah.
It's
okay.
not commutative.
Yeah. 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 And it isn't. Yeah, that's correct. Okay.
Trying to prove a false theorem is yeah.
All right. But even though it isn't commutative, it is associative. So
Yes.
yeah.
Yeah, I think yeah.
And we only need associativity. So
yeah,
it's all good. It's all good. But yeah, we were trying to prove something that is false for.
I think that's what is called a magma, isn't it?
What's a magma?
A set with a binary operation that is just associative.
That's a semigroup, no?
Yeah.
But without.
I don't think a magma has any property, just a binary operation.
Are you sure? Maybe, yeah, you're right.
Yeah. So this was pretty interesting. All super smart people. And yeah, even we can struggle with,
That's really the one that doesn't have.
That's why it's good to have a counterexample generator.
Yes.
Gives you this from this.
I think you need to use a dot before to like focus on the first case.
Well, if you look at example 3, I don't need to do that even. Oh, sorry. Yeah, from the link where from more tactics.
Yeah. No, I see what you mean. So it's just, I think, but that is strict. Okay. Yeah, I'm not sure.
And even this, like,
yeah.
Hey.
Oh, we had 2 buys, I think. Was that the problem?
No.
Oh, what changed?
The indentation.
Oh.
So what version of the...
Oh. To put the buy on the same line as the... Oh, yeah. All right.
Okay, so this is wrong, right? But if I think I can get it on the same line. There we go. This is also.
Oh no.
So usually they say they put the buy here.
Yeah, just put the buy here, but that's disturbing.
Yeah, right. Okay, but now let's see. Can I do it without the dots?
Surely, hopefully. Yeah.
Okay. Cool. Can I now use comma? No. Okay. So I can't use comma here, but I think I can at least use this. So this is the same as the dot.
Yeah.
And I wonder if I can go case EQ.
Mm.
Yeah, now I can do this. This is what I wanted to do. Like, and show, like, oh, look, it's so awesome.
Mm.
Because you can swap these around, it doesn't matter.
Yeah, that's nice.
But now, okay.
Also easier to read, right?
Yeah, and now I can actually see the goal. Okay.
Yeah.
So now I just need to evaluate it to be able to get to something that is kind of, if I can evaluate, I can be much closer to what I'm used to. Okay, now we're really gonna stop the stream. I've figured out what the button is for the stop live stream. There we go. Okay, goodbye.